name is Mr. Evangelista, and welcome to another episode of Evangelista Science. This is on 1-3, Reacting Masses and Volumes for the IB Chem SL curriculum. This is probably going to be a two-part video, just because of the calculations we have to do. But here are some of the topics that we're going to be going over. So let's take a look at some problems. So calculate the mass of carbon dioxide produced from the complete combustion of 1 gram of methane. Okay, so this is a combustion reaction with methane. The formula for methane is CH4. In a combustion reaction, we have a hydrocarbon mixing with oxygen, and this will always make carbon dioxide and water. We have to have a balanced chemical equation, so let's put a 2 here. That's 1, 2, 3, 4, so we'll put a 2 here, and that should be balanced. Okay, so we are starting with 1 gram of CH4, and we're trying to get to carbon dioxide. So the first thing we need to do is convert this to moles. And so for every 1 mole of CH4, this is 12 plus 4, so that's 16.04 grams. Okay, and so let's see, 1 divided by, this will give me 0.06 moles of methane. Okay, and I want to know how much carbon dioxide. So I can use the mole ratio, and where do I find the mole ratio? I find the mole ratio from the balanced chemical equation. So I can see in my balanced chemical equation I have 1 mole of CH4 for every 1 mole of CO2. So that means I'm going to have 0.06 moles of CO2. These units should cancel out. Should have showed that earlier, but 0.06 moles of CO2. Now they want to know the mass. So right now it's in moles. So for every 1 mole of CO2, this is 12 plus 16 plus 16. This is 44.01 grams of CO2. And so if we multiply these times 0.06, you should get 2.64 grams of CO2. I have 3 sig figs here, so 3 sig figs there should be good. Let's take a look at another example. So first off, let's talk about some formulas. So we have the percent yield and the percent error. This is useful for when we are trying to get a product and want to see how well our experiment or our attainment of that product went. You want to have, for a proper experiment, you want to have a high percent yield and you want to have a low percent error. Percent yield, if you go over 100%, that means you have added something to your product, something, maybe all the water isn't evaporated, something like that. It's very rare to get close to 100% yield. So if you're close to 100%, something is off, especially if you go over 100%. It's impossible to get over 100% yield. Okay, so let's take a look at this example. Nitrogen is prepared, so we have 2 ammonia plus copper oxide will make nitrogen gas plus copper metal plus water. We have 18.1 grams of ammonia, and it's reacted with 90.40 grams of copper oxide. Determine the mass of nitrogen formed. So this is going to be a limiting reactant problem, where we need to find out how much nitrogen can I get from this, how much nitrogen can I get from this, and figure out which one is going to run out first. So let's take a look. We have 18.1 grams of ammonia. We need to make this into moles. So there are 17.04 grams for every 1 mole of ammonia. And then we need to use the mole ratio to go from moles of ammonia to moles of nitrogen. Now, where do I get the mole ratio? I get it from the balanced chemical equation. It has to be balanced. So I have 2 moles of ammonia for every 1 mole of nitrogen gas. Brinkelhoff element right there. So you have 18.1 divided by 17.04 divided by 2. That gives 0.5311 moles of N2. Let's take a look at this one. So we have 90.40 grams of copper oxide. Same thing, for every 1 mole of copper oxide we have 79.55 grams. And then we need to use the mole ratio to go from moles of copper oxide to moles of nitrogen. So according to the balanced chemical equation, I have 3 moles of copper oxide for every 1 mole of nitrogen. So 90.4 divided by 79.55 divided by 3, I get 0.3788 about moles of nitrogen. The one that makes the least amount of nitrogen is the one that's going to run out first. So I have enough to make this much nitrogen. I have enough of this to make this much nitrogen. So this is how much nitrogen I can actually make. Okay, so this is going to be the limiting. Now, according to this problem, I want to find the mass of nitrogen formed. So I just need to convert this moles to grams. So for every 1 mole of N2, there are 28.02 grams of N2. So times 28.02, I get 10.6 grams of N2. I've got 3 sig figs, 4 sig figs, so 3 sig figs is good there. Okay, so if we were going to continue this problem, if I want to know how much reactant is left over after reacting the ammonia with the copper oxide, we know that all of the copper oxide is gone. It all went to the creation of 10.6 grams of N2. But we're going to have a little bit leftover ammonia. So how much of that ammonia is left over? Well, we can take the difference here. So we can go 0.5311 minus 0.3788 0.5311 minus 0.3788. We get 0.1523. This is moles of nitrogen. This is how much nitrogen I could have made if I had more copper oxide because I had an excess ammonia. And so I just have to go backwards to find out how much of this is left. So for every 1 mole of N2, I had 2 moles of NH3. And then for every 1 mole of NH3, there were 17.04 grams in the molar mass. So times 2 times 17.04. I had 5.19 grams of NH3 that should have stayed unreacted. The last part of this says if you actually obtain 9 grams of nitrogen, calculate the percent yield and the percent error. So we were supposed to get 10.6 grams from this nitrogen, but let's say we did this and we only got 9 grams, so maybe some of the gas escaped. Maybe some of the copper oxide remained unreacted. So a couple of things might lead to differences between our actual and our theoretical. So let's do percent yield. Percent yield is the actual over the theoretical times 100. So percent yield is our actual over our theoretical times 100. So we have 9 over 10.6, and we get about 84.91%. That's our percent yield. Let's do our percent error. Percent error is actual minus theoretical over theoretical times 100. And I forgot to add this in. This is going to be absolute value. So we have 9 minus 10.6 over 10.6 times 100. So 9 minus 10.6 divided by 10.6 times 100. And we get about 15.09% error. It's a pretty large percent error. We lost some product there that we were supposed to get at the end.